I'm convinced that the moisture level in a mushroom crop is only good once, and that is at the start of the first break. After that, you are out of the optimum. And that is the reason that people like Kai Begg and Kalberer in Switzerland and so on try to figure out what actually the loss on moisture is, and at the very same time, if you are losing that much moisture, the ability for the mycelium to move, to transport nutrients up to that point. So the question is can we substitute that water, what you are losing during first break? And again, we actually started years ago injecting water with diesel fuel pumps and that kind of things, but the concentration, that's part of the problem. And now certain growers use the technique by overwatering more or less the casing soil by purpose, and scratching more or less, make sure that that interface is open, and they actually water through the casing by purpose into the compost to replace the water lost during the first break. Tricky business. I personally don't like it because it's a little bit too, I think we need a little bit more experience going that far. But what I like, that somebody should set up some research like Rieber Rasmussen did, and I'm really wondering why nobody picked that up. Perhaps you know that Connie Rasmussen years ago did some experiments. He was using little boxes, 30 centimeters, 60, up to 1 meter 20. He filled those boxes with compost, put some casing on top of it, and grew some mushrooms, 1 meter 40. And then he added some radioactive phosphor here and figured out if the mycelium is able to carry moisture, nutrients, and so on up. And indeed, he could find that radioactive phosphor sometimes later in the mushrooms. So at least a mushroom is able, the mycelium is able to carry that water, food, by osmotic power and so on over that distance. Now, what I like personally, that somebody could do this, mark water added to the casing with some radioactive ions or so, and see if really that water goes into the casing. Dr. Staniek, but I can't discuss it with him anymore because he passed away, but Dr. Staniek even suggested that he was believing that the mycelium picks up some moisture from the casing and is using that to pick up some food and so on. That kind of action. Again, that are just, so, but somebody could figure out if you put that water, if indeed that water comes down. I'm a believer that because of the hygroscopic nature of compost, with a higher food, nutrient, salt concentration as the casing, that water is indeed moving, not just by overwatering, but just took from the casing and replace some of the water what's gone by picking the first break off and so on. Just based on experience on different farms in general, and research can prove that a little bit underdone compost can produce higher yields. But more that. It seems to be that more done is a kind of stabilizing effect. So the highest yields, most times we got on somewhat underdone, although that's very difficult to say what's underdone. If you talk about 3 o'clock, then it is maybe a little bit like that, talking about, yeah. And here again, there are perhaps a number of side effects. More done means better ability to compact the material, and maybe that has a side effect on temperature control, and that's maybe the reason, not so much the food, but, and as you mentioned, the water is maybe the limiting factor. But again, by a long year experience, the more done material seems to have a kind of stabilizing effect. Not the highest, not the lowest yield. The very same is true, I must say, with horse manure. We see the highest yields on synthetics, or I should say the non-horse manure, but also more like that. Horse manure, even if it is 20% or so, seems to have a kind of a stabilizing effect. And again, this is not scientific, this is just a question of what we picked up and whatever it is worth. There are also people who believed, and still believe partly, that all the primordiae for the entire crop are formed during flushing, the first, yeah? Based on observations, I'm an amateur photographer, and so what I did is I put the camera on a spot with a timer and made a picture every X hours automatically, day and night, and that for a couple of weeks. And then you see what you normally don't pick up, but because this is a static spot, 3 or 4 of those pictures are in the one of the versions of my book. And then you see that pins are formed after flushing. They don't make it in the first break. You see certain pins coming up, developing immature mushrooms, and still those pins are there. Marit was referring to that last time when she said you sometimes pick the entire first and the second and partly the third break if you ruin the beds that way. We found out that those pins sometimes even survive the second break. They don't die, but they're still there. And then sometimes you see that they turn into a little bit grayish, beige type, and then they are gone. And some of them still stay white and they show up the third break. So for a part, that theory is true. Okay, I'd like to spend a few words about the moisture level at spawning and also the ideal conditions during the vegetative growth, because later on we need that information if we talk about fructification and development of young fruit bodies and so on. What you see here is a full-grown compost after being 15 or 16 days in tunnels. There are a few things we should not forget during spawn run. We try to do first, after spawning, creating the proper conditions for the organism what we like to grow, for several reasons. First of all, of course, to promote the development of our agaricus. But the second thing is, and don't forget that, to avoid conditions where our competitors could live. We have to realize that there are, as you know, 80,000 or so microorganisms, and there is an enormous range of conditions
where they very specific like to grow. And we know that our agaricus, for instance, is using this part from all those conditions as being the optimum. And we know a number of them. For instance, the temperature. What is the best temperature for agaricus? Vegetative. You know? I think we know. Yeah? There is actually one optimum. The optimum for an organism is never something like this, but is most times something like that. A kind of a little range. But we know that for agaricus, that will be around 25. You can't argue about that. There are still people who say, yeah, I like it a little bit higher, or I like it a little bit... No, the optimum is the optimum. And we should not forget that at the very same moment that you go higher than that, you create better conditions for your competitor organisms. Many, many years ago, with our students, we always made a trip to institutes or farms abroad. And I went to Max Planck Institute in Germany with a number of students. And Professor von Zengbusch, at that time responsible for the research at Max Planck Institute, mushroom research, taught me a lesson. At that time, they were working on the Thiel procedure. You remember what I'm talking about, Thiel procedure? That means preparing a substrate without composting. How in the world can you grow mushrooms on not composted material? There must be, after a couple of weeks, that material must be loaded with all kind of competitor molds, green molds, yeah? Trichoderma, penicillium, or not. What do you think? Uncomposted material. Let's say straw, cottonseed meal, water, gypsum, and you mix that and you put spawn in it. What do you expect? Will the spawn grow? Try to imagine. You just chop straw, crush it, water, cottonseed meal, soybean meal, whatever, a protein type stuff, yeah? Some calcium, correct the pH, because the pH of straw is very low in general, 4.5 or 5 or so. It has to be 7. Why 7? That's another factor. Our agaricus is growing optimum in that kind of range. Again, not 7, but 6, 8 or 7, 2, that range. Other organisms have a higher, whether lower pH. That's another factor. Okay, now, answer my question. What will happen if you spawn uncomposted material with all the nutrients in it? Because you added cottonseed meal or soybean meal, huh? What do you think? How you think that compost will look like after 2 weeks or 3 weeks? What kind of color it will have? I think mostly green. Yeah? All kind of organisms will jump on that food. Why? The difference is if you don't decompose the material, then that material is not selective. So Dr. Thiel had a different idea. He said, listen, by composting, we are sacrificing 50% of our dry matter, which is a pity. And we do that because our competitors. So if you make sure that we don't have competitors, you don't need to compost that material. Okay, so crush that straw, add some cottonseed meal, water, gypsum, and sterilize it. That's the difference. So now there is plenty of food, but there are no competitors. Okay, now then the story. So Professor von Zengbusch showed us that kind of sterilized substrate. I'm not talking about compost now. And they filled 100 liter or even 200 liter drums with that material in such a layer. Can you imagine? In such a layer. Like this. Maybe 70, 80 kilograms of compost in such a layer. And then you saw a number of these drums, and there was a tiny plastic tube, and if you ask them what is that, they say, oh, that is the air system, the ventilation system. A tube like a pencil for such a drum of compost. And so Professor van Zeenmoes, you don't know him, but he passed away many years ago, but he was a tall person. I mean, if he was there, he was there. And so the first time I made a remark and said, but what about the temperature during spawn run in such a layer? At that time I was young, and he said, Peter, you should know better. I didn't know, huh? He said, listen, you study biology. Did you ever found, maybe beside lemmings, an organism killing himself? He said, one thing, if during spawn run that means during the development of agaricus, the temperature goes higher than the optimum. That's maybe, let's say, 28 or so, or below the optimum. That's maybe 22, that range. Then automatically Mother Nature will correct that. But yeah, we say as mushroom growers, but we often have seen that the temperature went up to 30, 33, because activity, he said, yeah, but not activity from agaricus, because that's impossible. So, if you create, or if you accept temperatures above 28, 29, then for sure you know that that's not created by agaricus. It is maybe initiated by agaricus, but then taken over by competitor organisms. And then he showed us a graph on the wall, and you could see the temperature in those drums went up 27, 27 and a half, stay there, comes back 26, 27, and that for weeks. Why is that? Because in that drum there was only one organism, agaricus, no competitors. So if you, and that we talk about water in the compost and controlling the temperature by evaporation and so on. If you have a problem controlling the temperature during spawn run, you better go back in phase 1, phase 2, because you failed to make a selective compost. The better, the more selective the compost is, you minimize the development of microorganisms competing with the mushroom, that will help the most. Now the first question is, why supplementing at spawning or later on at casing? Why not put that stuff in phase 1 and yeah? If you put it in during phase 1, phase 2, then those organisms, they burn it off for the biggest part. So what we do is, we try to make that compost as selective as possible. Then we add something attractive for almost all kinds of organisms, because if you are adding cracked soya beans or whatever, most of those products are based on that kind of products, protein-rich type, yeah, canola, soya, feather meal, blood meal, or something like that. you have to protect that, and there are several tricks. Some companies do it with formaldehyde, and Campbell Soup does it with a organic acid or combinations of that kind of treatment. You have to cover it so that you give the mycelium at least a couple of weeks time to develop, build up some what they call antagonism, natural antagonism, and then you free that kind of nutrients. So that's what I mean yesterday. The risky thing is if at the moment of spawning your compost is on the dry side, that's actually already telling you that you are a little bit off in the control of the process before that. If you are adding water and supplement, you break down that barrier from that supplement a little bit easier. Certain products do that a little bit more. As if you do that, if you add water to, for instance, the S39 or S41 from Campbell, I bet you it will end up green. Yeah? Okay, so that was the reason, and the reason that I'm not that fond of adding water at spawning is it is like aspirin. You try to correct the problem, and okay, it will help you for that particular moment, but you better go back and try to have that moisture level proper at the moment of spawning. So again, there are always stories around from, oh, I like to have that high temperature during spawn run. That's telling me that something is going on. Yeah, that's true, something is going on, but the wrong thing is going on. There is only one optimum, and that is the optimum for our organism, Agaricus, and that really is around the 25. Here again, you can do a better job in a tunnel as in thick layers. If you have thick layers, then of course you have to accept that if you try in a tray or in a bed, if you try to have the average in that range, you have to accept that in the center of the bed you will be a little bit on the top level, somewhere here, because the surrounding air is that much lower, because you have to control the temperature. Here again, if that compost goes wild, that is not because the activity of the mushroom mycelium, but that is the activity of your competitor organisms. And the combination of competitor organisms and a little bit drier compost, that's of course killing you, but that is exactly what David was pointing on, because a big part of that moisture, evaporation and so on, is then necessary to control the temperature. And so you are losing more moisture as the result of that. So I'm very much in favor of try to make your compost as done as possible, still handle it and so on structure-wise, but that is the main reason, to make it as selective as possible. If you create the proper conditions, you can do in 12 days, you can do more than, for instance, in 15 days, where the conditions are not optimum. And the very same for spawn run. And what Dave is saying, you see, the theory, but that is just theory, is that mycelium is, let's say, multiplying itself more or less 100% per day. So if you start with this, next day you will have that. Next day you will have like that. Next day you will have something like that. This theory, but can you imagine if you start with more spawn, then you start more or less that way. That will help. Up to a certain point where you say everything more than that doesn't do anything anymore for you. That's one of the reasons I'm not paid by a company like Sylvan or Campbell or Lambert, but I'm very much in favor of using enough spawn. And I call that a kind of insurance. I know yet you pay a few dollars more, but a compost after phase 2 is the most sensitive material for whatever organism. And our agaricus is one of the slower growing organisms. If you compare that with, for instance, green molds or so on, they grow in general 2.5, 3 times as fast as our agaricus. So we better give it an edge than and adding a little bit more spawn as just, yeah?
What's your definition of enough spawn?
Or you can express that different ways, but what are you using here? You talk about dry weight, or what is the most common thing, David?
Unit.
Yeah, but I'm sorry.
Unit, square feet per unit. Some people use percent of the dry weight, like supplement.
Yeah.
So I don't know.
You see, if you talk about units, what units? Some people say, I am using 7 cartons per room. Yeah, my God. First of all, what room and what cartons? Yeah? And pounds, that's also something, because some spawn makers, at least in Europe, not here, but they figure out that gypsum has a good weight, yeah? And so on, and all kind of tricks. But at least to come up with something, I prefer talking about a amount of spawn per dry weight, in the percentage of dry weight. And if you say a normal then, could be 2.5%, yeah, as a basic. And if you like a little bit more, of course, then you end up with 3 or, huh? Not that long ago, Mariet and I were visiting a relatively modern farm where they did spawn run in tunnels with 1-speed fans. So after spawning, you start that fan running, although there is no need for it. During the vegetative growth, there is no need for a lot of air movement through that compost. I mean, we know that during the vegetative growth, the CO2 concentration can be high. And we never have been able to prove that higher CO2 concentrations, and I'm talking about high, 10,000 parts per million or something like that in the compost, has a negative effect on the vegetative growth. So there is no need. The only reason to move air could be temperature control. And here again, if your compost is really well done, selective, then also for that purpose there is no need to move that amount of air. The only negative thing is then, if you still are pumping a lot of air through that compost, you are losing so much moisture. And again, at that particular farm, that was their main problem. They fill compost with 72, 73%, as they end up at the moment of casing 60, 59, and so on. I mean, so you have to work on that, and you realize that there are still growers over the globe who are using the rooms for spawn growth instead of tunnels. And here again, you can try to create more or less that kind of conditions in the compost, although you are not able to force the air through the compost, but at least you can try by covering that compost with paper or plastic. I prefer paper. It's more forgiving, but I know that there is more work, labor involved in putting it on and off. To create the optimum conditions and try, and that is again the point, try to limit the moisture loss, because that is for the big part. Huh? That even, and that is the advantage of paper, you can even daily make that paper wet, and because compost is hygroscopic, it will even pick up sometimes a little bit moisture. If the compost is on the drier side on the surface, it can pick up even some moisture from that paper. If you have plastic, of course, that's different. The only thing what you create with plastic is, it could be a problem that water underneath that plastic, as the result of condensation, because the room temperature is somewhat lower than the bed temperature, and that means where the air is touching that cold plastic, it will create condensation. And the metabolic products produced by the growing mycelium are more or less collected in that water. So if you measure the pH of that water, you will figure out that the pH of that condensation water on the surface is low. So actually what you are doing is you create a unfavorable layer between your casing and your compost. The surface of that compost is already a little bit, especially if you press or so that surface a little bit greasy. You have some little puddles of water. That water has a low pH as well. So you don't create the ideal conditions for the mycelium to move into that casing material. Therefore again, I prefer paper, but I realize quite well what the disadvantages of paper are in relation to put it on and off, and especially on tray farms is very difficult. Again, if you compare the same compost in plastic bags or in wrapped blocks, like you see here, then we figure out there are several farms who are doing the same thing. This farm, it's Kuhn in Switzerland, and Kuhn is preparing compost for his own farm. Actually, more farms than one normal in trays, one in plastic blocks or wrapped blocks, and he is also delivering that kind of material to other farms, selling those. And again, the yield per ton, the same compost, is always somewhat higher in the plastic wrapped blocks. That's telling us something, so that we can learn from that. That means that in that wrapped block, the conditions during vegetative growth seems to be better than in an open bed or in an open tray. That's one of the reasons, again, that the Dutch came up with plastic underneath their compost layers, because in their system, the metal racks with the nylon nets underneath, that is such a open bottom that there is a lot of evaporation and so on, and super spawning. And super spawning, maybe you know, but you have heard that term. What super spawning is you grow your own spawn, especially on a tray farm. You let's say normally you have 1,000 trays in a room. You spawn 100 this week, and for 2 weeks let it grow, and then those 100 are the spawn for the next 900 2 weeks later. Yeah? So you have a lot of spawn, isn't it? You mix in 10% full-grown material. The idea was great, but you mix in also a little bit green molds and a few nematodes, and they like that very much, because now you give them a month to develop. 2 weeks here, 2 weeks there, and all kinds of green can be the result. Yeah. A few words about casing. David covered already part of it. We all know that you need casing material for several reasons. One of them is no fructification without casing material. There are several other types of edible mushrooms who produce fruit bodies without casing, but our agaricus need that casing material. That is a complex thing in that casing material. After the mycelium has grown into, all kind of things going on, mainly microbiological things under the influence of bacteria, certain Pseudomonas varieties. There is a kind of action going on where bacteria break down certain metabolic products, including CO2 concentration changes, moisture changes, evaporation, temperature, that all creates fructification. That's one. And we can only create that kind of conditions in a layer of organic material. Water holding capacity is another thing, but for instance you could add a kind of inert material with a high water holding capacity if that was the only thing, but that doesn't work. Many years ago we did already that kind of experiments. So it has to be organic material because we need first of all the growth of the mycelium plus the development of a certain microflora, and the biggest part of that microflora is that kind of Pseudomonas bacteria. The water holding capacity is so important, later on we will spend a little bit time on that, because of, for several reasons, we have to create a certain air movement. We have to move quite a bit of CO2. We have to move quite a bit of heat, remove it from the beds and so on, to keep the temperature, the bed temperature under control, and therefore there's quite a bit of evaporation. Give you an example. Yesterday I all gave you this sheet. You have it still available? If you don't have one, Marit has some more. Just give you an example how much that can be. If you pick mushrooms from a bed, let's say a first break, a good first break, $10 kilos, yeah, not too bad, but possible. Then from a square meter, and David mentioned that already as well, you just take away 9.5 kilograms of water or something like that, just by picking mushroom, because mushrooms actually is water. But at the very same time, if you produce 10 kilograms of mushrooms, you at least are producing 10 times 1.2 gram of CO2. That means to remove that CO2, you need a certain amount of air. And last time we touched that already a little bit to give you some background ideas. If we accept that in the air in a mushroom house there could be maximum, let's say 0.08% CO2 as the you could also say 800 parts per million, as the maximum level, that way creating, let's say, a situation where you have somewhere on the surface of that casing material something like that, 1500 parts per million, yeah? Then we have to realize, if you talk about air conditioning, then instead of talking about volume, they give you most times the weight. We all know, for instance, that 1 cubic meter of air, we need that later on, if a block, you imagine a block of 1 meter by 1 meter by 1 meter. Here I have such a block. That's 1.3 kilograms. You know that? Yeah? Can you imagine? Here is it. This by that. Yeah? People say that's nothing. Oh yeah, that's 1.3 kilograms. What is that? That block. That's molecules. Molecules, CO2, oxygen, water, and so on. That has weight. We don't feel that, but that has weight. Now, the specific weight, if that block was complete CO2, then it was not 1.3 kilogram, but 2. CO2 is heavier than air. But in our air, there is only a certain percentage of CO2. In our fresh air, and I make it a little bit easier for you, there is approximately 400 parts per million, a little bit less, CO2. Yeah? So 1 cubic meter of air at a given temperature is a block like this. And in that block are certain molecules, water. Let me give that this. Oh, that's our water molecules. And there are other, let's say, oxygen, and there are others, gases, whatever. Oh, let me make them square. There we go. And we know exactly the concentration and so on, but there is one complication. The complication is that 1 cubic meter here now, given that the temperature in this room is 20 degrees, yeah, that cubic meter will be a bigger one if I heat it up a little bit. Why? Because these molecules are all active. They are moving. You don't see that, you don't feel it, but it really is. To prove that, you have such a empty balloon and you blow it up, and then it is a bigger. Who is holding that little rubber? The molecules. They are punching the wall and keep it. Yeah? If you lay that balloon in the sun, after half an hour you hear something. Bang! Because those molecules start moving faster and faster and faster, and at a certain moment the pressure is that high that the balloon can't handle it anymore. So what it is, if you are adding energy to those molecules, they are moving faster and they need more space. Therefore, a cubic meter of air at 15 degrees is not the same as the same amount of molecules, but now 25, because they need more space. That makes it a little bit complicated. So, if that is that particular cubic meter at 15 degrees, now we heat it up. What are we adding by heating it up? Energy. Not more molecules. No, what we are doing is we are adding energy, and then that block will grow into a bigger cubic meter, but the same amount of molecules. Aha, so there is more distance between the molecules. Aha, therefore, a certain amount of molecules at a higher temperature, there is more space to add water molecules in between. And you see that more or less on this list. The saturation point is telling you that, let's start at 0 Celsius. You can have as much as 4.8 gram water in the form of water molecules in a cubic meter. Yeah, 4.8 gram. You heat that same air up till 20 degrees Celsius, and then you see that air can hold 4 times as much water molecules. Yeah? You heat it up till 50, and you see that it can hold almost 20 times as much water molecules. Now, the implementation of this, we touched that already yesterday a little bit by talking about moisturizing the air. People in charge of controlling the environment, the climate in the growing rooms, should have knowledge about this. They should have that kind of information on the wall so that you realize what you are doing. Again, now back to that 10 kilogram first break. During the development of that kilogram, you are producing CO2. How much CO2 you are producing? We know, if you calculate certain things, you are producing more or less 1 gram CO2 per kilogram of mushrooms per hour. You can measure that. You can measure the metabolic activity of a human being. Yeah? If I measure your intake and your output, then I measure the amount of CO2, and from that I can calculate how much carbohydrates you are burning at the moment. Sitting here and listening, I am burning a little bit more, and if I run 3 times around this building, at least if I could make that, yeah, then I was even more burning, and so my CO2 production would be higher. That means you can measure the activity of an organism by measuring the CO2 production. Okay. Now, the production of 1 kilogram of mushrooms, there are that many carbohydrates and so on involved that we produce more or less 1 gram CO2 per kilogram per hour. Higher temperatures, if we speed up that process, it will produce more CO2. Not per kilogram, but in the time. You slow down the process, like in the caves, lower temperature, you slow down the entire process, and therefore the production of CO2. Not per kilogram, but in time. Okay, now the trick is that we figure out, hey, look at this. In the air is already, in fresh air, is already 400 parts per million. You can't change that. That's Mother Nature. It is a little bit less, I know that. But. And you told me that you don't accept much higher than 800 parts per million in the aisle, in the growing room. That means 1500 or whatever on the surface of the beds or something like that. If the specific weight of CO2 is 2, that's true, then you talk about, you see that here? The difference between 2 times this is 0.8 gram, and 2 times this is 1.6 gram. Now, dit is not exactly 1 gram, it is a little bit more. Dit is not exactly 400 parts per million, it is a little bit less. So the end conclusion is that the production of CO2 is more or less 1.2 gram or 1 gram CO2 per kilogram, and you can take away that amount of CO2 by introducing 1 cubic meter fresh air and send it out in the back. You follow me what I'm doing? I bring in fresh air with that level of CO2, 800 parts per million or whatever, and I send it out in the back of the room with that level. That's approximately whatever. 400 parts per million, that's more or less 800 parts per million, 900 parts per million. The difference between that and that is more or less 1 gram. Aha. Huh? If you study psychology, and then you have to study quite a bit of German literature, and in that literature, as they tell you sometimes that young people, the Aha-Erlebnis in German, the aha experience, that at a certain moment you see certain things and say, aha. Huh? So, that aha is, say, now I see a relation between the need for fresh air. If 1 kilogram of mushrooms is producing 1 gram, more or less, CO2 per hour, and I like to have that level in that growing room constant because I can't handle higher CO2 because lengthening the stems and so on, and I can move, I can transport more or less 1 gram with 1 cubic meter of air, then I find a relation. The need for ventilation is more or less 1 cubic meter fresh air per kilogram of mushrooms per hour. If you have a first break on the beds expecting 10 kilogram, the need for fresh air movement to control the CO2 is at least 10 cubic meter per hour. If you have a growing room 300 square meters, yeah, then you have on the beds more or less 3,000 kilogram of mushrooms, yeah, developing. That means 3,000 grams CO2 production. That means at least 3,000 cubic meter of air what you have to bring in and out to control the CO2. I'm not talking about controlling the temperature. That's another story. But at least, let's continue. 3,000 cubic meter of fresh air. That has nothing to do with the air circulation. You follow me? Circulation is another story. What is the purpose of circulation? The purpose of circulation is different. Circulation gives you uniformity. Yeah? Have the same temperature here as there and so on. But that is not telling you anything about ventilation. Ventilation means fresh air in, spent air out. Circulation means that the circulation can be 3 times as much as the ventilation is. You follow me? Yeah? Okay. 3,000 kilograms on the beds, that means we need at least to replace 3,000 cubic meters of air per hour. And now the story. Why do we need casing material with that high water holding capacity level? Can you imagine? You live here, Canada, Wellington Farm, Leamington, whatever, where the farm is, on a reasonable cool day, let's say, situation, let's make it a little bit, let's say you have 11 degrees outside, Celsius, and let's say that particular moment the relative humidity is 60%. Now, first of all, if the relative humidity is 60%, what does that mean? That means that in the air, at that given temperature, 11 degrees, there is 60% from the amount of water what could be in that air. What is the maximum what can be in that air at 11 degrees? 10 gram, yeah? You follow me? That's what they call the absolute humidity. Relative means in percent, 60% from the amount what could be. So what is actually in that air? How many grams? let's say 7 grams is in the air. Okay, that is the air what you bring in the room. Now you bring it in the room, and in your growing room the temperature is let's say somewhere between 17 and 18. That means the maximum what could be in that air is 15 grams. You follow me here on the list? Yeah? You follow me? If it was 17, it was 14.4 gram. If it was 18, it was 15.3, something in between. So it could be 15 gram. But in the growing room, the relative humidity is not 100%, but is maybe, what do you like, 85? Okay, let's go for 85. How many grams is that, 85% from 15? You have a calculator. We don't, that doesn't work anymore, so we need a calculator. Eh? What is 85% from 15?
12.7.
Oh, 13, oh, yeah, whatever. So the reality is that with that temperature, there is, in fact, you said 13 gram in it. Yeah? And now you see what the situation is. In the room, the temperature was approximately 17, 18 degrees. The relative humidity, you told me, was 85. And the absolute amount of water, 85% from the 15, what is the maximum, is 13. That's the situation in the room. But now you bring in 3,000 cubic meter of this. So there is a deficit. Every cubic meter will take away at least 6 gram. You see that? Because that air coming from outside was colder, and even not that cold. In winter it could be, if it was 0, then instead of 7 gram it was half of that or something like that. So every cubic meter can take away the difference between the 7 and the 13, which is 6 gram. 3,000 times 6 gram is 18,000 gram, is 18 liter, just as the result of that per hour. 18 liter per hour. And the day for that mushroom had 24 hours. And 24 hours times 18 liter is, more or less. Yeah? Did you figure out? I'm sorry?
Around 400.
400 liter. Yeah? Okay. So, I'm not talking about controlling the temperature yet, just to keep that CO2 level constant, given 11 degree outside, given 60% relative humidity, you are losing already 400 liters a day, just by evaporation. If it is colder than 11, much worse. Can you imagine if you talk about cool down, flushing, or whatever, if the situation inside was 25, then you talk about almost about 23 gram instead of 15, so the deficit will be much bigger. And you are losing much more water. And that will be one of the reasons that talking about after casing, we like to bring up the casing material as wet as possible, without creating problems with water leaching into the interface in the surface, creating there less good conditions, nematodes and all that kind of things. Okay, why do I prefer to bring that casing material on as wet as possible? Why did I say yesterday that I prefer casing soil number 1 or A? Now you saw why. It was the most heavy material. Do you have the idea, it was 85, was it? 84, 85, something like that. Yeah? Did you think that that kind of casing material put on a bed should create a problem with water leaching out? No.
I don't think so. Now the advantage is, if you start already that level, then you don't need immediately next day or so to water, because it gives you some time for the mycelium, if this is the real world, that the mycelium starts recovering. You don't need to water immediately. Plus, if you have caking material in that casing material, David was mentioning that, you only have a couple of days time left over to bring that moisture level up to that point. And if you start too low here, then, and you don't like to water immediately after the application of the casing material, then you really are running out of time here, because the time is so limited. Therefore, I like to have material with a good water holding capacity, a good water holding retention, and bring it on as wet as you can handle it without creating the negative aspects of leaching, etc., etc., under normal conditions. If compost is off, that's a different story, but that is not the normal situation. Talking about the layer, David was more or less indicating that the layer, the thickness of the layer, is not so important. That's true within limits if the environment is the ideal one. Why, yesterday I mentioned that, why can you grow mushrooms in the caves in France without a casing layer with a high water holding capacity? Why is that? Because first of all, you hardly move any air. Yeah, here we have to move the 3,000 cubic meter minimum, because of the CO2 production, because we are packing that room 5, 6, 7 layers. That's one. Yeah? Plus, we grow the mushrooms 16, 18 degrees, bed temperatures, 22, 20, whatever. And in the caves, I told you, the temperature is 11, 10.5, sometimes 12, depending on what kind of caves you are talking about. So you slow down the entire, that's different. Huh? Another thing is that, can we put the lights down a little bit? Let's see where I'm talking about. Yeah. Again, I made that picture in Indonesia. This is one of the farms. This is perhaps at 6 o'clock in the morning. And this is the best air conditioning system you ever have seen, because it is designed by the Lord. Yeah? The Lord's air conditioning. I mean, the natural, you see how hazy, yeah, it is. The best thing what you can do, and what we did during the night, open the doors. Slow air movement, the temperature almost ideal, and the relative humidity, I don't need to tell you what the relative humidity there is in the mountains. I mean, you can't compete with any computerized system. Now, can you imagine that in that situation, the water holding capacity is not such an important thing here? Why not? Because you are not creating such an enormous drying effect and so on and so on. And if you have, instead of 5 layers, 3 layers in such a growing room, that will help also. So sometimes we create our own problems. That's okay, as long as you realize what you are doing and this kind of calculations, and you should do that with your people going back to the farm and say, hey, come here, listen, do you realize what you are doing? Yeah. Because if we talk about the differences, if the CO2 is really related to the production, do you believe that, what I'm saying, that the CO2 production is really related to the production? Is that makes sense?
Yeah? If that makes sense, do I talk nonsense if or give me your opinion about first break, second, third? If I write down here, 10 kilo, first break. Okay, talk about your neighbor's farm. I mean, huh? Makes it easier. What is the second? Come on. If you're...
6.
Huh? 6? Okay, 6. And the third? 3. 19 kilo. Do you survive? Okay, it's just an example. We easily could make it 12 and 8 and 4. That's fine. But that's more or less what it could be, yeah? Now, that means that if your ventilation system is based on what it should be, then in this situation you have at least to give 12 cubic meter per hour fresh air per kilogram of mushroom. That's, and I don't know how big your growing rooms are. If you have 500 square meter growing rooms, that means in this situation you have to introduce 6,000 cubic meter of fresh air, more or less, to control the CO2 concentration. And then the 6,000 you can calculate with your guys and say, okay, what is the temperature outside? Oh, 7. And you say, okay, that air can have maximum, more or less, 7-8 gram water per cubic meter. You are introducing 6,000 of those cubic meters, and you bring that in your growing room where the temperature is 18. That means 15.3, but it is not 100%, it is maybe 80 or 85%. That means it is not 15 but 14, but the deficit between the 4 and the 14 is almost 10 gram. That's 60 liters per hour, and that 24 hours we are losing quite a bit of water. But okay, that's the consequence. But it also is telling you that in the third break, 3 or 4 kilo, let's go for it because we did that there as well, then that's not 12, that's 2,000 cubic meter instead of 6,000. 1/3. If you control the amount of fresh air just manual by damper, I know exactly what you are doing. We did that for years. In the first break, you put a damper like that. Yeah? That means, whatever that means. And then in the second break, maybe you move it a little bit like that, and you think, so that's it. And you do exactly the same, because if you open that kind of dampers a little bit, then it is doing 80%, and whatever you do, that doesn't make any difference anyway. True or not? That's what you are doing. So you are wasting quite a bit of energy and water, moisture, unnecessarily. So try to go with your guys over that. Also the other way around, of course. Yeah? Condensation. If your mushrooms have a certain temperature, and during the night you bring in some cooler air, and next morning you are wondering why the blotch came from, it could well be, you see, you can calculate yourself how many degrees you have to lower the temperature before you reach that 100% point. Yeah? If you have 92% or something like that at 18 degrees, then you see if you go to 17, you have already 100%, that means condensation. And quite often during the night, that kind of things can happen. So I'm a strong advocate of going with the guys who are responsible for your watering and controlling the growing rooms over this kind of basic thing, so that they have a better understanding what they are doing.
Do you remember yesterday, and we still try to do that in growing rooms as well, humidifying the air with cold water? You are drying the air, but you don't believe that until you calculate and say, God, yeah, that's true. You are drying the air by spraying cold water. You bring that air to the saturation point. Cooling is the very same. I have seen tunnels for spawn run, and here is the tunnel, and now you can answer that question yourself. Here is the compost in that tunnel, and here is the plenum. And people say, hey, I am losing so much moisture because I have to move so much air through the compost, and I don't like that, so I build in a cooling coil. You follow me? So instead of moving all the air through the compost, I build in a cooling coil somewhere here. Let's say here is the cooling coil, and I move the air through that cooling coil, and now I can lower the air speed. No, that doesn't help you, because you have to take away the same amount of energy. So what that cooling coil is doing, the air comes out here, let's say 27, and because the limited amount of air what you like to push through the compost, you have to cool it down here, maybe up to whatever, 20 or even 15, and you can calculate then whatever you do, but you are losing the difference between the amount of moisture. That will be almost 100% saturated. If your compost is really aggressive because the layer is too thick or the compost is still a little bit on the green side, yeah, then you have to battle those temperatures. Especially if you are supplementing and so on, 24 in the beds and 17 in the air. Yeah. That means quite a bit of air circulation and fresh air to control the situation. Okay, if you can handle it with water, maybe not too bad. Worse is the other situation. If there is no any activity, you know that, then you quite often will reach that saturation point. I'm talking now about mushrooms on the beds and so on. Let's say in the second and the third break, if you are losing all the activity and the temperature between the beds and the surrounding air is almost the same, then there is no activity, nothing is going on. So that balance between those two, that's the trick. By experience in general, we know that if you grow hybrids and your compost temperature comes below 20, 19, you really are losing your activity, and it is very difficult to get it back. So we try always to have that compost temperature at least in that 20 plus area, 19, at least some differences between air and bed temperature. We don't like to water too early because as in the period that the tiny primordia are developing, we like to stay away with water. That means that casing material has to bridge that period first of all until the young mushrooms have the size of a large pea, then we can start watering. Now, quite often, if we started too low here, we are already behind here, and we have to keep up. At a certain moment, we have to stop because we don't like to water too much on maturing mushrooms, and so here we have another period where we have to rely on a certain reserve what we build up. And again, here if you have 6 or 5 centimeters material with a good water retention, that's much more forgiving as if you have 3 centimeters and you say, oh gosh, I wish I, The the changes in moisture levels in that 3 centimeter are much bigger as in the 5 or 6 centimeter. That is the reason that I'm very much in favor of a firm casing layer. But again, we don't talk about centimeters, we talk about the goal. And the goal is have enough reserve to bridge that kind of period without, and David, you are right that you mentioned that, if you think that that casing material is dry by feeling, you are far behind already. Yeah? And we also measured in Holland the capacity, the cooling capacity, if that casing material reaches a certain level. You follow what I'm saying, or what I try to say? As long as that casing layer on the surface has, for instance, a moisture level or 72% or 75% plus, then it has a good cooling effect because there is quite a bit of evaporation. If you reach a point, let's say 65, then that cooling effect drops enormously because there is not that much moisture available on the surface anymore, and from that moment on you suffer. We try to limit the number of hyphae. We try to limit the vegetative growth in that casing material so that we only have a limited number of strains coming up. The second thing is we can try to limit that again by the moisture level, but also by the other factors being the temperature. In general, the lower the temperature, the more shocking, and keep that lower temperature for a longer period of time will create more pins. The more the dilution, that means the lower the CO2 concentration in the air in comparison to compost casing, the more pins. The bigger the shock between moisture levels, and I'm talking about evaporation now, that means lower relative humidity, the more pins, and the opposite. So, and of course the strain, the characteristic of the strain is playing a role, but we more or less grow the same type of strain, so that's not so much a big deal anymore. Years ago there was more difference. There still are differences. If you grow a U3 type strain, a pure white or so, there is more tendency to overpinning as if you grow, let's say, the real U1 or one of the derivatives of U1. So there are ways to try to control the number of pins. If you start somewhat late, you let, like here, I showed that slide before, but those guys, for the Dutch guys, dit is boekel. Yeah? Those guys, because they like that number of pins up to the point overpinning, because they are working towards mechanical harvesting. So they let the mycelium come as high as possible, even on the surface. That means that in such a situation you have to control the environment very well, because it's that mycelium, those primordia are very sensitive for less good conditions, but nevertheless they let it come up to that point and then shock it so that they really have a number of pins, and that's then the result. Okay, you still could pick some mushrooms quality, but will be very difficult, but they don't give a damn about that. They say that's great. They talk about 18 kilo or 20 kilo in the first break. They just cut them off and that's it. So there are ways to influence that if you know a few tricks, and this slide gives you some indications why we prefer somewhat less pins. in combination with harvesting technique and so on, because what I said this morning, it is not so important what the conditions are in the corridor, in the aisle, but what the conditions are there where the mushrooms grow, microclimate. And you see, and it is just a situation, but based on measuring temperatures and CO2 concentrations, in reality, the temperature and the relative humidity and the CO2 concentration in the room similar, but if you measure in a situation like this, overpinning, the CO2 concentration underneath, in between, in a cluster or in between, will be much higher. The relative humidity up to 100%, talking about blotch and that kind of things. Temperatures higher, and you don't need to be an expert. You can put a thermometer, and maybe you did that quite often, in a cluster, and you will see that the temperature is higher and the CO2 concentration is higher. So, therefore, I don't like that situation too much. Let's try to avoid that overpinning, and part of it is uniformity. Uniformity as the result of spreading the mycelium uniform by deep scratching, by cacking, or combinations of cacking, deep scratching, and that kind of things. I think this slide gives you that total picture. I'm still a strong believer that you need a certain casing layer. I prefer a somewhat thicker layer because that is more forgiving. That casing layer, moisture level, is for the biggest part a question of controlling temperatures by evaporation, the necessary ventilation to get rid of your CO2, but also if that casing layer, the moisture level, is high enough, it will have a kind of a replacing effect, because you are losing the biggest part of the water. What you take away with the mushrooms will come from the compost, but there will be some replacement from the casing material. Not so much from overwatering by purpose. I still think that is a tricky technique, but more by just the difference, what David says, energy level. If here the moisture level is high, I just give a figure higher than in the compost. The moisture level in the compost will be lower every break, because mushrooms are taking away moisture, and for a part it can be replaced by the moisture from the casing layer. That's the main reason that I prefer that somewhat thicker layer, and in general, especially prior to the first break, to the maximum moisture level. Now, we don't need to argue too much about relative humidities. Relative humidities, of course, have a big impact on the evaporation level in combination with the amount of air you are moving, but we can't go that much higher because of blotch, and we can't go that much lower because of scaliness and so on. So the relation between the amount of air, that is one of the reasons that I really urge you to work with this kind of information with the guys who are in charge of watering and ventilation and so on, because it is important to don't overdo. Every 1,000 cubic meter fresh air you give unnecessary, you take away a lot of water and so on, and you are disturbing the microclimate unnecessarily. Yeah, watering, of course, here you see that kind of watering machinery. What we did at a certain point, but the slides are not all that clear here. The newer farms sometimes put an extra rail beside their beds instead of putting the lorry for harvesting and so on it. They even have the same watering tree and put it on the rail and so on so that it moves more easily. I must say one thing, talking about water management. We touched that already prior to lunch. We had a discussion with a well-known grower. He said, I don't understand that you can use that watering tree because it's impossible to do a good job. I say, why not? He said, because we are watering selective. I give a little bit more here and a little bit less there. Now the first question is, do you really? I mean, as a demonstration, yes, but in reality, I see who those guys water. Huh? I mean, that's the way they do it. Yeah. He even developed a certain technique. He said, we go in the morning, for instance, if you give twice a day some water, in the morning we go around that way, and in the evening, if we have to do a second one, we go from the other side because, and so on. So that sounds very sophisticated, but again, that's not so much reality. So what we did is we developed a bed with a wire bottom and just casing layer on a net, but underneath was no compost, but cans, where we try to learn the students how to water and see how uniform they did. And the guy who was arguing, actually it was Kuhn in Switzerland, he did the very same. And it didn't take him too long to say, Peter, you are damn right, because you are as ununiform as you can be by doing it that way. And so that could be sometimes a tool for you if you try to convince some people that that machine is doing a much better job as you normally do by hand, really. It's much more uniform. And if you say, yeah, but I'm watering selective, then maybe what Kuhn did, he didn't, not so sophisticated as we did it, but he had only a few empty cans in the bed. If this is the surface of a bed, he had an empty can here, an empty can here, and then he let the guy water and measure the amount of water in those cans at certain spots, and then he figured out how ununiform we actually are watering. So I'm glad, David, that you taught us that there is also a horizontal movement of water so that at least the water can spread that way. Yeah? A little, yeah.
A final comment from Peter Vedder, which I think is important. A reminder of sorts to keep alert and be aware of what needs to be done each and every day.
It is not so much that we don't know what to do, but get it done.